let's get to the practical aspect of things. So it's all very fine to say, well, I want to, for example, if I want to measure the S11, so of a one port, so this is basically a transmission line which you connect to some Z. In a lot of electronics, you will or test related topics, you will find this DUT or DUT as people like to call it often, and the DUT stands for device under test, right. And the idea is that you want to be able to measure. The simplest case of measurement is you have one port and you want to measure it, right. And even with a one port, even though there's potentially no issue with stability, you can't go and put the voltmeter and ammeter right at the two terminals of the impedance you want to measure, right. I mean, presumably there is some distance between, I mean, this is the measurement equipment is some kind of box, and this is Z DUT is some tiny thing somewhere, and you need some kind of cable or interface to go from the box to the DUT, and therefore you have some kind of transmission line, right. So what you want to do therefore is to measure. Remember, for a one port, you want to basically be able to measure the ratio of, I mean, if you measure V minus by V plus, okay. So if you measure V minus by V plus, you basically know the, well, what all you, I mean, okay, now actually let me ask you the question. Okay, well, this is our setup, right. How do you think we should go and measure, or we can go and measure Z DUT? What all do you think we can do? I mean, this can be done many ways. What do you think you would do? Okay, that only gives you, okay, I mean, yeah, tell me exactly what you would want to do. Okay, let's say we know Z naught, and is that all that's needed? Do you need something else or what? TD, okay, fine. So he says, well, I need to know Z naught and TD, alright, and then what? Come on, folks. Okay, well, he says, okay, let's see, if this is V plus, what is this? V plus e to the minus, j omega TD, right? And what is this? I mean, we'll use the short form for this. This is gamma times V plus e to the minus j omega TD. So what is V minus here? Gamma V plus e to the minus 2 j omega times TD, correct? So if we were somehow able to measure let's assume that we are, I mean, we have a transmission line and we are able to measure the forward going and the backward going waves, right. That's equivalent to measuring what? I mean, how will we, I mean, what do you think, conceptually, how will you measure V plus and V minus? You have a transmission line, do you want to measure V plus and V minus? What do you think you should, you could do in principle? In practice, it's how you do it is another matter, but in principle, what would you do? What do you need to know? Yeah, so basically remember that if you want to measure the voltage and current, I mean, you want to measure the forward and backward going waves, at some point you measure the voltage and the current, and recognize that V is nothing but V plus plus V minus, and I is nothing but V plus minus V minus by Z, right. I mean, even in SPICE, this is a good way of measuring the forward going wave and the backward going wave. Basically, you have it's using voltage controlled. So basically, V plus is nothing but voltage plus Z naught times current by 2, and similarly V minus equals V minus Z naught I times 1/2, correct. So, if you measure the voltage and current at a point, you will be able to find out what the forward going and the backward going waves are. And measuring voltage is easy. I mean, in practice, if you, at least in principle, measuring the voltage is very straightforward. What do you think you can do? Well, you just need to stick something in parallel with that node and you will be able to find the voltage. Measuring current, on the other hand, is, what do you have to do to measure current? You put something in series, so you have to cut the transmission line and put your ammeter there, right. So, obviously, this is only okay in the textbook, it is not okay in practice, right. So, if you want to find a current which is flowing like this, right, how will you, what do you think you can do to measure that current without actually cutting the wire? Pardon? Yeah. So, basically you couple an inductor somewhere and so that you will get a coupled, you basically use mutual induction, right. Okay. So, in reality it turns out, I am not sure I will have time to discuss it in this course, but it turns out that it is possible, and the principle is this: eventually if you want to find the positive and the forward and the backward going waves, you have to do voltage plus Z times current and voltage minus Z times current. The only question is how you accomplish this, right. It turns out that there are if you use coupled transmission lines means what? Well, you have a conductor like this and you have you put another so for example, let us say you have a conductor running over the ground, over a piece of a shield of metal, okay, and you have another conductor like this, okay. Now, these two guys are also talking to each other. There is capacitive coupling because of, well, that two conductors separated in space, there is some capacitance. There is also inductive coupling because of there is going to be some current induced in the second one due to the first one, right. So, in principle it is possible to measure both current and voltage flowing on a line, right, without actually physically going and cutting it to measure the current, okay. And so, that is, and eventually they use the coupled voltage and the coupled current to go and compute V plus and V minus, right, and that contraption which is used to do it is what is called a directional coupler. Alright. So, a directional coupler is basically a contraption that basically you can use to go and figure out what the forward going wave is and what the backward going wave is, alright. And the principle is at what do you call a 10,000 meter view from the sky is what it is essentially doing is computing V plus Z naught times I by 2 and V minus Z naught times by 2, except that there is no calculator, it is punching, right. It uses Maxwell's equations to do this computation. So, the idea is basically like, the idea is therefore, if we are able to separate out the forward and the backward going waves, right, which we will do using this magic device called the directional coupler, then how will we find the impedance? What will we do? Oh, well, it's we know gamma v plus e to the minus 2 omega d, and we know v plus. So, taking the ratio, you get gamma times e to the minus j 2 omega T d. Well, T d is known, right, and omega is known because, I mean, you know the frequency at which you want to measure, right, and therefore, this is known, okay, which basically means that you can find so find gamma, and once you find gamma, how will you find z dut? Oh, well, this is nothing but z dot minus z naught by z dot plus z naught, all right, and all this, I mean, so once you know gamma, you can go and you know z naught already, so you can find z. Does it make sense, folks? Well, what are the problems with this approach? Pardon? I can't hear you. I mean, he's saying, oh, you must, I mean, you're sloppy and you don't make the measurement properly. Yeah, of course, if you don't measure properly, nothing will be correct, right? But the assumption is that, you know, either you do it properly or you hire somebody to do it properly. Okay, all right. So that's you know, what do you call it? Where are all the problems where you can get? Where all can you get errors? Yeah. Well, we need. Remember that the reflection coefficient you measure. What dimensions does it have? It's got dimensions. It doesn't have any dimensions. The z dot, what dimensions does it have? Well, it's got ohms, right? So whatever you do to transform, you know, gamma into z dot, right, will have something inside which has got dimensions of. You have a box, you put in gamma, you are getting z dot, right? You are putting in something dimensionless, you are getting ohms. So inside the box there must be something where you are multiplying by ohms, and that happens to be the z naught here, right? So if the z naught is not accurate or not exactly known, okay, then you will have trouble, okay, and likewise I mean, we said that the length of the line is you know, is Td, and well, if the Td is not accurately known, okay, well, if you have a cable in the lab, well, you know that it is kind of, you know, what the Td value is, but you don't know it exactly. So if Z naught and Td are not known properly, clearly our estimation of first our estimation of this guy will be wrong, right? Once you that basically means the gamma that you get will be in error. If the gamma is in error and Z naught is in error, then the Z dot you measure will be in error. Correct? Well, we have a problem, right? So what do we do to fix this problem? What do you think we can do? So basically, what he says is very good. So basically, his his idea is, oh well, we don't know Z naught and we don't know Td, correct? Okay, we don't know them exactly at any rate. So let's try and figure them out. Okay, so every time you're making a measurement, right, before you actually make your measurement, let's try and figure out Z naught and Td, and use that Z naught and Td obtained, you know, just before you plug Z dot in, right, in these formulas, and then you should be able to get Z dot exactly. Correct? Does it make sense? I mean, it's obviously more complicated than simply plugging and playing here, right? But I mean, hey, you know, if you don't know what Z naught is and if you don't know what Td is, you know, be prepared to do some work a little harder. Correct? Okay. So in general, therefore, let's look at this, you know, what we actually have. So we have an unknown 2-port between correct. So, we will be able to measure the reflection coefficient here, correct, which is equivalent to saying we know the impedance looking in here, okay, but we are trying to find the impedance there, but we do not know this, the box that stuck between the unknown 2 port and what you are actually measuring, correct, alright. So, what do you think we should be doing therefore? Well, we do not know, I mean obviously with an unknown 2 port you can't make any progress. So, you have to convert that unknown 2 port into a known 2 port. Now, so how many parameters do you need to characterize that unknown 2 port? I mean in general for a 2 port you need 4 parameters, but what is so special about this unknown 2 port between your measurement equipment and the actual Z dot? It's it's basically it's passive, right, and time invariant, and therefore it is I mean it's reciprocal. So, how many parameters do you actually need? You don't really need, in general you need 4, right. Reciprocity ensures that, ensures what? Well, the S11, the S21 and S12 of this 2 port are the same, or the Z12 and Z21 or Y12 and Y21 are the same. So, we need 3 parameters. If you need 3 parameters, how many equations do you need? We need 3 equations. So, therefore, before you put Z dot, right, we need to find the 3 the 3 unknowns of the 2 port, right. So, therefore, before measurement what do? You terminate this 2 port with, I mean instead of Z dot you put in how many impedances must you put in there? We need to find 3 unknowns, guys. We need 3 equations. So, you basically put in 3 test impedances there, right, okay. So, in other words, we first find and what comment can you make about 3, and what is your choice of 3 test impedances? Well, you can say I will put 50 ohms, 51 ohms and 51.1 ohms. Is that a smart way of doing things? Pardon? Why can't, why can't I put 50 ohms, 50.1 ohms and 50.2 ohms? Pardon? I can't hear you, man. Will become? Hey, you have a computer, 3 equations, 3 unknowns. I mean, how difficult can it be? Pardon? Measurement precision is a problem, right? I mean, you will forget, I mean, when you try to invert those matrices, if you put 50 ohms, 50.1 ohms and 50.2 ohms, right, then they will become, the equations will become ill conditioned, because you pretty much have the same equation, right. Just copying the equation 3 times doesn't make it. Copy and pasting the equation, saying I have 3 equations now, doesn't help, right, because the rank of that matrix is basically still close to 1. Okay. So, you want to choose impedances here which are within quotes as different from each other as possible, right. So, in other words, the reflection coefficient you get must be as different as possible. So, what do you think the best choices are? Well, when you terminate it with a short, right, where the reflection coefficient is of the impedance is, if you have a short circuit, what is the reflection coefficient? -1. If you have an open circuit, it is +1, and if you have nominally something which is we know that unknown 2 port is kind of like a transmission line. So, if you have Z naught, then you basically have 0 reflection coefficient, right. So, the first experiment is to measure Z short, right, where you short port 2, then the second experiment is you find Z open when you open port 2, alright, and the third experiment is you find Z, I don't know, Z50 when you terminate it with Z0, which is, I mean, the standard impedance that is used in microwave work is RF and microwave work to connect up blocks together is 50 ohms. So, in the Z0 is 50 ohms. So, so basically from Z short, Z open and Z50, and if you know those, you will in principle be able to find the right, you will be able to find the Z parameters, for instance, of this unknown 2 port. I mean, if you do not like the Z parameters, you can find the S parameters, it does not matter, right. But bottom line, you will be able to, you know what that unknown 2 port is, right. Then what will you do? Yeah, then you put, finally you put the Z dot, and then right, and the resulting impedance you measure is Z unknown, and from since you know Z50 is Z open and Z short, you will be able to find Z11, Z12, Z21, which is the same as Z12 and Z22, right. And once you know this matrix, I mean this matrix, and you know Z unknown, you will be able to figure out what Z dot is, alright. And this is this process of finding this unknown, or characterizing this unknown animal between the measurement port and the Z dot, this is called calibration. I mean, you might be wondering, hey, you know, what is this guy talking about, right? You know, in my electronics lab, you know, all the time I was measuring, you know, a resistance by taking a multimeter, and then, you know, in fact, the multimeter was on my neighbor's desk, and I ran these 4 feet long cables, and then, you know, measured the resistance, and the resistance turned out to be okay, all right. Okay, so, so how come we need all this complicated thing now? I mean, why did all this suddenly become important? I mean, are we smoking dope, or is it like, you know, what seems like a trivial thing is, you know, connecting a multimeter across 2 terminals? I mean, should it be this complicated? Huh? I understand we need to do it, but I mean, in your electronics lab, when you were measuring, like, you know, a resistance, did you do all this? So how do we reconcile that? At low frequency, which is equivalent to saying omega equal to when you are doing this at low frequency, I mean, low frequency basically means that, I mean, omega is close to 0, then what happens? What happens to the transmission line? When TD equal to 0, right, that basically means what? Well, it just behaves like a short circuit, and then, you know what you measure, even 4 feet away at DC is the same as you know, I mean, it does not matter how sloppy you are, correct? Okay. Of course, if the transmission line is not, I mean, if your cable has got some finite resistance, then there will be an error, right? And to kind of fix that error, I mean, you know, if you want to be really careful, you terminate the other end of the cable with a short circuit and see what you measure on your multimeter, and then you connect your unknown resistance, and then, you know, the difference will give you the actual resistance that you want to measure, correct? But if the cable is lossless at DC, right, then all this doesn't matter, because if Td is equal to 0, then, well, this is V plus, this is gamma times V plus. So, the voltage here is the same as the voltage here, right, and similarly the current here and the current here are the same. So, it does not matter that you have a long cable, right. Only when that omega times Td product becomes large is when you start to have errors in measurement. If you simply stick a cable and say, oh, I will continue what I did to do what I did in my basic electronics lab, where everything was running at half a kilohertz, right. If I try to do this when at say a gigahertz, right, okay, then if you have a foot long cable, right, a foot long cable has got a Td of how many seconds? Okay, a foot is how many meters, guys? 1/3 of a meter, right, and speed of light is 3 to 10 power 8 is only when when you have free space men. Typically 1.5 is a reasonable estimate, right. Okay, so you do the math. So 1/3 into whatever, 1.5 into 10 power and 8 meters per second. So that's what 1.5 into 3 is about 5, right. So it's something like 20 nanoseconds, is it? Okay, I hope that's right. Okay, so 20 nanoseconds times a gigahertz is times 2 pi is, so that e to the minus j2 omega times Td is a significant phase shift. It's not 1, all right. So as frequencies, I mean, this I hope, so if say if I mean, and as you can see that omega times Td for at a gigahertz is several multiples of 2 pi. So if you want that to be a short fraction, a small fraction of 2 pi, which corresponds to the phase of one wavelength, then that the length of the cable better be very, very small in relation to the wavelength, correct. Now, if you are now working not at 1 gigahertz, but if you are working at 60 gigahertz now, right, what qualified as a small distance at 1 gigahertz now qualifies as, can be a is effectively looks electrically 60 times larger if you are working at 60 gigahertz, right. So at high frequencies, this if the dimensions of the physical circuit that you are working, I mean the physical dimensions of the circuit you are working with are comparable to a small fraction of the wavelength, is when all these distributed effects become important, right. So you should understand this very clearly, right, because I don't know about you, but when I was studying all this in my EM class 30 years ago, right, I always used to wonder, how come when you move from basic electronics to the transmission line course, even things as simple as measuring an impedance all of a sudden become so complicated, right. I mean, were we doing things wrong in the basic electronics class, or is this guy simply making a big fuss out of nothing, right? Okay. So as you can see, there is method to this madness, right? I mean, there is a reason why these things are important, right? So at high frequencies, and what is the meaning of high frequency therefore? This omega times Td is, I would say, a significant fraction of, I would say, like maybe 1/10, let us say, right, arbitrarily. I am just saying 0.1 is bad enough, right? Okay. And what is Td in terms of length and omega? In 1 Td, I mean, remember that frequency is nothing but omega by 2 pi, correct, and basically in 1 TD, I mean in 2 pi over omega seconds, you will basically, the wave will move by how much? One wavelength, right. So, basically this TD is related to I mean which is related to the physical length of the cable, is eventually related to the wavelength of light at that frequency, correct. So, this omega times TD product being not sufficiently close to 0 basically means the physical dimensions of your transmission lines, or the circuit that you are working with, become comparable to the wavelength of light at that frequency. The moment that becomes it becomes comparable, then all distributed effects, I mean then this notion of the voltage here, I mean, hey, I have shorted these two nodes together, right. It does not make any sense, because the voltage here and the voltage here are different, and therefore, all this lumped element approximations all become unworkable, right. Okay.